Dear conference participants, we present to your attention a report on the topic Intelligent System for Planning Treatment of Retinopathy with Laser Technology. The research focuses on retinal laser photocoagulation, a key treatment method that allows for the destruction of abnormal blood vessels. In the context of ocular health, one significant concern is diabetic retinopathy, which can lead to vision impairment or even blindness. It occurs when high level of blood sugar damage the delicate blood vessels in the retina, the light-sensitive tissue at the back of the eye. Accurate and early diagnosis, along with effective treatment, can prevent blindness in more than 50% of cases. One of the most effective treatments for diabetic retinopathy is retinal laser photocoagulation. Retinal photocoagulation is known to use a laser to seal or destroy the abnormal blood vessels and prevent further damage to the retina. The therapy for diabetic macular edema is a complex process that includes both conservative and surgical laser techniques. The primary treatment modality for diabetic macular edema today is laser photocoagulation of the macular region of the retina. The procedure involves applying a series of controlled microburns or laser photocoagulates in the edematous area of the retina. These photocoagulates are applied individually or in a pattern of specific shape or with a pre-planned position followed by the application of the generated plan of the retinal image. The most preferable approach is an even distribution of photocoagulation spots, ensuring they are placed at maximum evenly spaced distances from each other within the edematous area while avoiding contact with blood vessels. Applying these photocoagulates with prior planning is conducted under the control of an automatic laser beam position system allowing for precise treatment. Nonetheless, a significant challenge in the photocoagulation procedure is a rule the manual assignment of the photocoagulation map, often resulting in a, or even application of photocoagulates within a restricted region of the fundus, called macular zone. Furthermore, manual placement of photocoagulates considerably extends the duration of the operation. The procedure of applying a series of coagulates to the fundus of the eye is governed by special conditions. Photocoagulates must not overlap with the macular area, major blood vessels, and the healthy regions. The coagulation zone should encompass the maximum area of the exudate region. In addition, photocoagulate region should not overlap to ensure that the microburn does not exceed acceptable limits. The primary goal of the investigation is to develop an algorithm for solving the problem or dense circle arrangement based on mathematical programming based packing method in existence. The aim is to satisfy the requirements of optimal filling of the specified region with circle and acceptable execution time. One of the predominant limitations inherent in established algorithm designed for the placement of photocoagulants lies in their tendency to generate uh, planning of accommodation pattern solution. Recognizing the imperative need to enhance the coverage of photocoagulants on the fundus, we advocate for a novel approach that leverage the principles of mathematical programming. This innovative method aims to overcome the drawbacks of conventional algorithm by adopting a mathematical programming framework. Unlike existing solutions that often result in the sparse patterns, our proposed method seeks to optimize the distribution of photocoagulants on the fundus through a systematic application of mathematical programming principles. The formal description of photocoagulant placement in the treatment area employs the well-known method of phi function. The placement region has in general an irregular shape, which can be described as the union of non-intersecting non-convex polygons separated by vessels walls. Each non-convex polygon is represented as a convex polygon from which a finite number of convex polygons have been removed. Segments are used to model the boundaries of non-penetrating vessels, as shown as in the figure on slide 5. The treatment domain D is represented as a union of non-convex polygons, as we can see in Formula 1. We assume that burns are modeled as circle C with radii R. The condition of placing of circles, taking into account distances, is represented as Formula 3. And packing cylinders into domain D to meet distances limitation sigma is defined as Formula 4, where 3 and 4 are normalized free functions. A general problem of placement of coagulants GPPC is stated as follows. We need place the maximal number n of circles with radii R in the treatment domain D such that the placement condition 3 and 4 are satisfied. To solve the problem, a two-stage approach is proposed in which at first stage circles are estimated that are guaranteed to be located in a given area. At the second stage, a series of problems are solved that allow us to find the maximum number of circles that can be placed in a given area, taking into account all the restrictions. Taking into account the partition 1 for the treatment domain D, problems GPPC is decomposed into P independent subproblems PPC for each subset DK. Let's denote as NK with asterisk as the maximum value of circles for each subtask. To find this value, the method of dichotomy is used on the interval AB. To determine whether it is possible to place n circle in domain DK, the problem 5-6 is solved. This problem is a mathematical programming problem which can define maximum sum of radii of placed circles. The presented algorithm not only serves as a tool for the effective distribution of circles during photocoagulation, but also implies that the best coverage of treatment area is achieved through the collection interaction of elements. To test the effectiveness of development algorithm, we solved the problem of placing radiation zone for an area considered in work 1. As a result of applying our approach, it was possible to achieve a more dense placement of irradiation zone by increasing the number of placed circles on 2 circles, as we can see on figure depicted on slide 7. Conclusions. The novelty of this work lies in the development of computer intelligent system utilizing an algorithm grounded in the mathematical programming to optimize the placement of photocoagulates. The research considers effective treatment strategies for diabetic retinopathy, a serious diseases that can lead to vision impairment or blindness. Retinal laser photocoagulation, which allows for the destruction of abnormal blood vessels, is identified as a key treatment method. The study highlights the importance of evenly distributing photocoagulation spots within the edematous area, avoiding contact with blood vessels. The potential of this approach is further enhanced by the development of an algorithm for optimal photocoagulate placement based on mathematical programming. Future research will focus on a more precise formal description of the photocoagulation domain, giving opportunities for even more accurate and effective treatments. The continuous refinement of this method is crucial for advancing the field and improving patient and outcomes. Thank you for your attention.